going to look at these approaches for larger scale data management. And I said earlier that I split this into two. We are looking at traditional approaches and modern approaches, and probably look at strengths and challenges for each, and probably get off a bit how you can choose among each, and how we chose ours, and probably how you can choose in your cases. And lastly, we shall look at one case example, just briefly. There is a work that we did with Conrad that it should perfectly fit here, but also we can do a little bit 5-minute demo of the tool that we are developing at Unisalento. So generally, from summing up this, our ultimate goal is just to explore the available approaches, but again, understand the challenges, the underlying challenges for these approaches, and also see the possible options. Now let's get to understand the basic terms. We obviously already started to discuss about data, and now there is a rising term that we speak about modern data. What is this modern data? We usually sum it to the data that we are currently generating, considering the tools that we have, the machines that we have, the number of devices that we are already connecting them to internet. And the nature is usually complex and fast generated, because most of them, they generate data in real time. And also, the modern data are considered to be coming from various sources. And also, considering this aspect, they also give a rising demand for managing and processing them. Usually people discuss them by looking at data, or literally the concept of big data, by looking at the V's at the character of the new data that we generate. So generally we have the like 3 V's for big data, but this can be extended into many V's depending how you're looking at data, what kind of data, and what kind of data you are working with. So as I said, we have the 3 V's, but you can extend these into so many of them, because some of people are also exploring this in terms of vulnerability. They say that for data to be fit into modern data, or to be called big data, it also has to have some element of vulnerability. Data should not be vulnerable to attacks, but also should be valid into a specific use case. For data to be called big data, it should be directed to a certain use cases. And there are so many other V's. But our concept here, if you remember our topic, is large scale data management. So there are also different perspectives of looking at what is large scale data and what is big data. Generally, there is no much of differences, but when we speak of large scale data, we expect that this data comes with very huge volumes. So big data is being looked at number of V's, but large scale data, it has this volume item. Data has to be huge in terms of size, but also it does not abandon the other V's, but at least the volume must be there. When we speak of this modern data, we're also looking at structured and unstructured data, but also some resources are extended into looking at ability for us to process them. When we process, we should get a certain meaning from them. Well, now why are we having these conversations? Why should we be speaking of data management while we already have several approaches to manage data? Because now we are generating data and we're already storing them. Now, why should we discuss it? One of alarming challenges is the amount of data that we generate. This is one of very big concern. And I feel like most of data that we generate, we're not even using them. We shall see into some of basic examples. And there are several reasons for that. It could be just because we do not need them, or we just cannot access them. So we shall look at these examples. But we can see we are already generating a lot of data, and the projection shows that we are also going to generate a lot of data, even more. Well, the perspective in energy systems is also the same, considering that now we're deploying these smart grids, and also we have approaches to integrate sources of energy and several other measures to digitalize energy systems. Whenever you speak of digitalizing energy systems, we are speaking of generating, curating, and storing this data. Now, there is always a question of data management and how we can achieve this. And because we have these increasing data sources, which also come in different types. It could be not a serious problem if we have an increasing amount of data, but they come like in the same shape. Probably we would not have been discussing this, but data is coming in different types, in different shapes. For instance, the use of smart meters is already generating large amount of data, and there are several concerns around this. Like smart meter data, they also have element of personal identifying data. So there is an aspect of security, and also the size of data itself is already a lot. Now, these data that we are generating, we are not able to access them. Like only 2% to 4% of smart meter data is currently being used. So you see, there is also a lot of data which we think might be important because we mostly do analysis based on this large amount of data, but also historic data. We need all of them to get information from them. Now, considering these challenges in energy systems and general perspective on data generation and data management aspect, what are the major concerns that we are having? We can split this into 3 or 4 groups. Concern number 1, now we are not speaking about data storage, like we can store all of them because we have capacities to store the data, but we do not have time to read them. Reading the data is a challenge. If we want to read them, like there is always a consequence in terms of time. If you want to read like all the existing data today, probably you have to take for 1 million of years to read all of them. So it depends, different use cases, but whenever you have this huge amount of data, there is an aspect of time which you need to consider on reading them. Another aspect is that data are too big, that they cannot fit in main memory. And because we cannot store the data in main memory, so we are forced to opt for storage, to store them in a disk. Now, when you store the data in disk, there is an aspect of input and output costs because you need to consider the communication or the cost of writing the data into a disk and also reading data from the disk. Now, what are the options currently existing, like to most of practitioners, is that some people choose just to throw away the data that sounds to be not of importance. Well, and we believe that most of data could be of importance. At least we can do some analysis from them. Another concern is that data is also too big to fit in a single machine. There are several options that have been deployed. Some people choose to store them in parallel computing or distributed environment. Now, this one also comes at the cost of communication, because when you have the parallel communication system or the parallel system or distributed system, you have to consider always how do you communicate among the parallel running systems or the distributed systems architecture. Now, these concerns, they raise a huge demand for innovative data management approaches. And in this case, we are looking at the possibilities of using the existing data management approaches, like the traditional relational database management approaches or other approaches, because back before this, we are storing them in terms of files. And so if you want to download a certain section of data, you simply download the file and share to people who want to see them or use them. Now, should we dive into approaches of larger scale data management just quickly? And we are going to start to traditional data management approaches. One of the predominant data management approach is the relational databases. This has been there in market. And as much as I'm concerned, it's very, very good, very efficient. You can model your data, you can store them. It's very easy to like retrieve them, and you can get the data that you want because you can specify a certain query statement and you literally get what you want. Now, if you look at this, we have a simple example for user and the consumption data, right? So in terms of a user, you might have these few details like user identification information, the contract related to consumption, and also the power of the house and other attributes. But those attributes should be the attributes that identify a user. And on the other side, you have consumption. And this consumption we are fetching in terms of a certain household, for instance. But each consumption, that means it's fetching data, it's linked directly to a certain user or a certain household. Now, what are the concerns here? If you want to model this into relational database, for each relation or for each table, you need at least one identifying key. We call it a primary key. And you can see here in the user table, I've labeled user ID to be an identifying key, right? And so by being so, this primary key can also be used to map relationship with other relations. Now, in the conceptual, we are linking, in the consumption table, we are linking it directly with the user ID. And you can see here, in the consumption, we have a combination of user ID and timestamp as the primary key. Why? Because we want for each consumption, we need to map exactly when was it collected. And so it will be collected over time. But also there are other attributes like user ID as said. You can also add some more attributes that can be linked directly to consumption. So that is the basic principle of mapping relational databases. Like for each table, you need to identify a primary key that will be the identifying key for that table. But also, if you are to link two relations or more, you need a foreign key. A foreign key should be referring to a primary key of the originating table. Now, one question might come, because this example is looking at consumption into a certain household. What if you want to map consumption looking at a specific device? That will require you to remap the database, and that's where relational databases requires you to do some little bit of work. But after doing that, you can access this data easily. Now, the question might be, where do you map it to? Like the device, should we link it to a user, household, or should we connect it to consumption? So these are possible questions that you think of before designing the relational database. Now, the challenges that comes with the relational databases is that, well, they have these strict relationships. As you model your data, you need also to consider these strict relationships. And so you have that they have to fit into a certain pattern. We call it ACID property. So, well, if you implement them correctly, then you can retrieve the data that you want. But the challenges that they come with relational databases is that it's very difficult to manage the growing data. As you get the data, as the amount of data grows in relational databases, it becomes difficult to retrieve them. But also as the data gets complex, it's also difficult to model them in terms of relational databases, because the relational databases store the data in terms of rows and columns. So if you're collecting different types of data, it becomes difficult, or in some cases, probably impossible to map them as a relational databases. And with growing data also, remember, we are considering now we have all these varied sources and they're increasing, and we have real-time data. Now, managing relationships in terms of relational databases is getting impractical. That's why most of people are choosing other approaches to storing data. But even if you manage to store them and model, running queries to huge data sets can also be a challenge. Because of these complexities, you have so many relationships that a query has to consider before fetching the results. Usually, if you want to scale relational databases, they are forcing you to do vertical scaling, add more of computing resources, and that there is always a limit, right? So there is a limit to which you can grow further. So yes, considering these challenges, one of the approaches that came to address this is the use of data warehousing. Now with data warehousing, you are able now to have different databases and merge them together. Of course, there are methods to extract this data from several sources, and then you transform them into your underlying architecture in the data warehouse, and then load them into where you want. One advantage of data warehouse is that you can do analysis based on historical data because you have so many of them. And also, it does not diverge much from relational property. Data warehouse have a schema to which all the data components that are stored into data warehouse have to follow. So you might have different sources, like here, I'm presenting the customer database. power generation databases and infrastructure databases. That's just random examples, could be anything. These are mapped into a global data warehouse. But whenever they go through ETL process, I mentioned this extract, transform, and loading into the data warehouse. Whenever they go, this process is actually, it's the process to make sure that they abide to a predefined schema on that data warehouse. So it can go there, you can store, and you can do analysis. But remember now, we still have the predefined schema that we need to follow. So data warehouse, yes, it can accommodate several sources, but there is also some limitations. You always need to consider a schema as you write your data. These, well, may lead us into several failures. The number one, it could be just technical challenges, or in some other cases, complex architecture becomes really difficult to map them into data warehouses. But one of a very huge concern is meeting user requirements, right? Because now we are preaching data warehouse can solve your problem, and so many users are coming to your platform and they store data. But when they come to retrieve, they say we want data A, B, C, D, and data warehouse could not fill the requirements. Now that also is a big challenge, because now requirements are changing, right? And businesses does not know that you do not have a certain methods to extract this data, or there is limitation with your underlying platform. So meeting user requirements now, it's getting even more difficult, because businesses collect all kinds of data. All this data needs to be stored. Well, as a diverge to data warehouse, because we have this limitation, a bit of schema, the requirement for schema, and it is still in the structure of you need to store and manage the structured data. Is a divergent route from this, there are data lakes. Now, data lakes is like a data warehouse. It collects data from various sources, except that it allows the storage of unstructured data. And in the data lakes, you do not have to think of schema when you are storing data. Like you have your data just dump into the data lake. The schema will be considered when you retrieve the data, because you have this pattern. I want certain data from this period, When you get the result, that is your schema that you wanted. But we don't consider schema as we are writing the data. Now, the implementation of data lake benefits from several implementations, including low-cost commodity hardware like Hadoop. We are going to look in a bit about Hadoop. What is it? What's its limitation also? Now, with the data lake, it can accommodate this structured data plus all other benefits of the data warehouse, except for the structured data, because now we do not consider structured data anymore. We're storing unstructured data. Now, the limitation with the data lake is that data discovery becomes a little bit a challenge. It's not impossible. You can fetch them, but it becomes a challenge. Also, extraction and cleaning efforts becomes very huge, because you stored almost everything there without considering the structure. Now, when you get the data, you have to consider cleaning them to fit into what you want to use for. Also, integrating the data sources in the data lakes is also another big challenge. And again, this goes back there. We do not have the structure of data. We just dump there everything. One of the challenges that implementations face is versioning of this data. Remember, it's just like a data dumping place. So you store everything. At the end of the day, versioning of these databases is also a challenge. Now, quality in these kind of structures is a nightmare, because you have all varied structures. So we cannot speak about data quality anymore. And you do not expect to get consistent data throughout your implementation. Like someone would be dumping user data or person identifying data in a certain structure or in a certain file format, and another one will dump in there in totally different format. So you're all looking for user information data, but they're all coming in different structures, because that's how they're stored. One result that is led by these challenges is that we are generating the data swamps. Data swamps is unmanaged data lakes, and not because we do not want to manage them. In some cases, it might be because it's very difficult to manage them. It's merely impossible. Now, recently, we are having these approaches also, NoSQL data management approaches. They usually come into 4 models. You have the key value database model, we have document model, you have graph, and you have common-based model. NoSQL by itself, there has been several names. People are saying no, not only SQL, or there has been several terms, right? But its main goal is to diverge from the restrictive measures that we have in relational databases. And so we need to store data without looking at the structure, or at least have a mix of unstructured and the structured data that is falling into semi-structured. Let's look a bit into this form. Now, when you implement your data by using these NoSQL databases, remember, in relational databases, we say that if you want to manage growing data, you are forced to grow vertically, right? That means adding additional computing resources. But with NoSQL, you are allowed to grow horizontally. Your system itself, it allows you to manage these growing data sets. Also, they do not guarantee ACID property, which is a requirement in the relational databases, because the relational databases have to follow these strict rules. That is not a requirement with the NoSQL databases. Now, if you implemented the NoSQL database, if you implemented them in a centralized environment, then scaling could also be difficult. So apart from them just supporting horizontal scaling, but if they implemented in a centralized environment, also scaling, there is a limitation to which you can scale. Okay, yeah, perfect. Now, a brief about these, I hope you can see this table. A summary brief about these models that we have in NoSQL databases. We can group them by looking at performance, scalability, flexibility, complexity, and functionality. This table should guide you to know what you can choose in terms of implementing your NoSQL database. Now, when you want to implement using key value, that's the simplest design, because you just simply have a key and a value. And so everything is like working perfectly. You expect a very high performance in terms of storage and how you can retrieve the data, but it's very easy to scale because there is no this predefined schema. You can just identify key and the value, and then flexibility is very high. Complexity, we do not have complexity at all when you're dealing with key and value data. And functionality, well, that can be variable because it depends with the use cases. What do you want to achieve? That goes also into so many other designs. And we have the graph database model in the NoSQL. This is one of interesting data models that exists in the market. One of the reasons is that it is not typically a structured data and not completely a structured unstructured model, but it's somewhere there it is semi-structured. So there is a structure to which you need to follow, and it supports growth. You can grow the data as much as you want because it identifies the data in terms of nodes, which identifies the entities, and then you have edges which maps the relationship between the nodes. So there are several options around NoSQL databases. One framework that I also said we could look at it later is the Hadoop framework. Now, with Hadoop, it can support the storage and processing of very large data sets. And good thing is that it can support also distributed fashion. When you have a distributed environment, we are speaking of improving fault tolerance because now you do not have a centralized system to which you rely on data management. And so because data sources are distributed across different processes, so fault tolerance is very high. Now, the Hadoop implementation benefits from a cluster of computers that combine storage and processing power together. Now, this gives you a high level of scalability because a single computer, the system can be considered from a single computer to thousands of clustered machines. So you can see the power of it because you can support up to 1,000 machines, but also you can store very, very large amount of data. Its structure is comprised of 4 main components. The Hadoop has the HDFS, which is literally for data storage and data being stored in terms of files. And then you have Yarn for resource distribution. You may consider this like it's the operating system of the Hadoop framework, because it's literally based on its main role is to make sure that resources are managed properly. And then you have the MapReduce. Its main goal is to split or at least distribute the huge processing tasks into small tasks that can be processed into a distributed computing node. And then there is Hadoop Common, which manages utilities and libraries that needs to be used by whole of the system, or at least the connected machines. But what can go wrong with this system? We already have distributed environment, and also we are supporting very large scale data. Let's look at what can go wrong. First of all, not really made for medium-sized or small-sized companies. When you're deploying Hadoop, we are considering that you are operating under very huge amount of data, and it's for big businesses which are managing very large-scale data. And also, it's typically not a relational database management system, and not of the kind, because we are storing data here in terms of file. And so you do not expect to have the benefits of relational database management in the Hadoop. Now, data in Hadoop, this is also one of the challenges. Data in Hadoop cannot really be updated, but you just append data files one on top of another. So yeah, these are one of limitations in terms of Hadoop, but you can see it has very huge power because of its distributed nature, but also can store this large amount of data that you want to process. One approach that I thought is very important to look into is the Google file system, or some other people abbreviate as GSF. This was initially developed internally by Google to meet their own internal requirements. Now, its design, basically, it's built on top of distributed systems, and it is considering the distributed environment. And also, that was the main motivation when developing the GFS. Okay, well, perfect. One of very common component in GFS that is also available in Hadoop is that in the design, one of its principles is that component failure is considered as a norm, because in a distributed environment, when you have, let's say, 1,000 machines, a possibility that 1 or 2 machines will fail in the process is very high. So this has always been considered as a norm. Machine failure should be considered as a norm in distributed machines. Also, one of the things that are considered in GFS is that files that are being stored in GFS are considered to be very large, but they are also mutated by appending new data rather than overwriting the existing data. So you don't overwrite the existing data, but you have to append into existing data. Well, with GFS, apart from its maturity, now there are a few limitations, just a few of them. First, it is originally made by Google, and so its main goal and what it can achieve, it was literally looking for Google, but you have room like to adjust what you want to do. And also implements a single master node. This, I feel like this is one of a huge limitation, because you have this master node that oversees all of other nodes that are joining into the system. When you have a single master node that has a certain task, you're introducing a single point of failure, because when that node is failing, then yeah, the system is also at fault. Again, with GFS, consistency is very limited. Well, as a departure to these systems, because we're speaking of Hadoop, GFS, and then relational data warehouse, data lakes. Now we have cloud computing. This is also common among most implementers. And one of reasons for this being a popular choice is that you do not really care what's there, right? Because managing resources is up to the host. So you just dump that in the cloud and that's it. Now, this is considered as an escape route to several providers. And because also it gives you flexibility of accessing data, like you can access wherever you are. In so many other implementation, it's very difficult to access data from where you are. Now, there are a few challenges with this, apart from having data dispersion, because also managing data consistency in the cloud environment can also be challenging. Vendor locking is one of the biggest challenge, because you implement your service, you store very large amount of data into a certain provider. When you feel like this provider is not giving me enough, switching to a different provider cannot be practical, because you have to consider all this amount of data, modeling again the new architecture into a new provider. So most of people just choose, yeah, we can just tolerate. Also, cost racking is one of the biggest challenge, because the cost goes high as you store more data, and we have already seen that we are still generating a lot of data. There is also a question of security. This is also looked like everyone has their ways to look at it, but to me, it's like you do not know the underlying infrastructure, and you don't know if what I store there is being shared to other members or not. You cannot really be sure of any underlying architecture. Now, to get rid of the vendor locking, some people opt to try a polynimous approach. This is implementing at least two cloud providers on managing data. But there is one hurdle with this. Managing data becomes even more complex, because now you have two providers. And so whenever you want to look at your data, you always have to consider, this data I get from provider A, this data I get from provider 2. It becomes a little bit of a challenge. Well, another approach that I thought is very important to look into is the peer-to-peer data management. Now, in this case, we do not have the master node, but every system is joining as a peer, and so they can send data. They have power to act as a server, but also act as a client, because you can request data, and so you can send data as you feel like. You all have this autonomy. Well, peer-to-peer by itself have been existing for a while, but we have this term we call modern peer-to-peer, which comes with the support of massive distribution of location of these peers. Now we do not have to consider location of them, like it can be located geographically very separated, because there have been limitation back in time. You might call like peer-to-peer system, but peers have to, for example, exist in one single land, right? But now that is not a concern anymore. But also heterogeneous nature, because now peers are considered, I mean, peer can be even your personal computer. And so by this case, it even increases the heterogeneous nature of the peer-to-peer system. But also there is an issue of volatility. There is much of flexibility in this design. These modern peer-to-peer systems aim to achieve several features. One of them is the autonomy. Like peers should be allowed to live and join at will. There has been limitation, like joining and leaving the system has to be limited, and it has to be like back in time, it had to be looked carefully, like you have to really to manage it, because in some cases it could disrupt the system. But now peers can join and leave the network at their will without any hurdles. But these peer-to-peer management approaches, they also aim to improve query cost. I mean, in terms of time. I mean, when you run a query into a peer-to-peer management system, we expect to get response in literally very little amount of time. Also efficiency, which is looked in terms of number of queries that you can run into a system into a given amount of time. But also quality of service, which is a user perceived efficiency. This can be in terms of completeness of results, because there is always a concern of time when you're fetching data. And so how complete results we are getting. But also there is an issue of data consistency and availability, also query response time, as we've already looked at it. There is faulty tolerance, and lastly, security. Now, one of the very important features that we have in peer-to-peer data management is how we can discover and look up the peers in the network, but also how we can merge the results that we have into peers, and lastly, data replication. Its basic architecture, it could look something similar to this sketch. Like you have a place where you submit local queries, right? Yeah, it could be a local query or a global query that has to be managed by the data management layer. Data management layer has also to be passed to a network overlay, which also passes the query to all other peers. Remember, this structure is the structure that has to be adapted to all the peers that are available into a network. Now, this is just the basic structure. We shall look at the demo how really it works. Now, if you are to sum up the challenges of the large scale data management, we can group them into three. Number one is the scalability. Scaling data management approaches can be a challenge, but also data quality is also an issue. If you look at existing data storage management we have, or data management approaches that we have, especially we are looking at data accuracy, consistency, and also compliance depending on user requirements. But again, one of the very serious challenges accessing this data is merely a nightmare because we have so many of them. And so reading them is also another difficult challenge that we always have to look into. So if we are not able to access these data, that means some of data can be stored in silos in places where you cannot reach them. We have seen the results of data swamps that has been led caused by the data lakes. But again, if you have data in silos, we expect also inconsistencies with the data that you are fetching. This also has to come, of course, with incomplete patterns. In some cases, you might fetch data, but the data items comes so incomplete. Now, because also we have these diverse data sources, and so data integration is also a challenge. Looking this again into energy domain, we have already looked at the amount of data that we're generating. So there is always already challenge of the amount of data that we're generating, but also reading them, managing them. Like you have to go through a lot of procedures if you want to really read them. But there is a concern also of data integration, because now it's like there is no standardization. Like if you're storing data into a certain architecture, you need to follow this format, or you need to communicate data using a certain protocols, or we do not have that. So reading them, managing them into energy system generally, it becomes a challenge. Like everyone is working with a certain data, and all of these data are in totally different shapes. Now, okay, should we take a break? Probably. Now let's dive just a little bit quick looking into what is needed versus what we have currently. So getting a picture around this, I've extracted the data exchange reference architecture from the European Union. What do they really want? So they split this in terms of layers. They have a component layer, communication layer, and other upper layers. I hope you can see this diagram well. But at the component layer, in terms of data exchange solutions, there is a huge insist in data exchange platforms that are looking at distributed data storage. So that's what we literally need, because now data sources are expanding almost everywhere. And these exchanges should support bilateral data exchange. I mean, each connected component should be able to read or write the data from the system. This mostly you cannot get them from client server architecture, because client always have to request for services, but not bilateral data exchange. But if you go to communication layer, there is a huge insist on the predefined data format, let's say, or the protocols that you are sharing the data. Now, this is DERA 2.0, just an overview for it. If you go to DERA 3.0, it's just like the same architecture. They have simplified it by representing the local machine and federated machine, like what you can do with them when you have both of them, because now we insist of having this distributed architecture. So it's very important to consider what to do at local machine level and what to do at the federated machines. So, well, this is just a summarized version of the DERA 2.0. Now, our simplified version in terms by looking at each layer, at component layer, We are looking at distributed data exchange by having these distributed solutions, but also solutions that consider privacy in the process, because in the energy systems, somewhere, somehow, we are collecting data that has personal identifying information. And in terms of application that is in the component layer, we are also looking at the tools that support large-scale data storage. And in the data formatting protocols, like you can choose any of them. One of the important aspect in the use of protocol and data formats is that you need to choose data formats or protocols that are widely used and widely acceptable, but most importantly, they have to be open source. Like we should not be going for data formats or protocols that you need to do some subscription or something like that. Now, in summary of all of these, distributed approaches is the direction that we all need to consider. One of the reasons is that data are stored locally, like in distributed system, data are stored close to where they are needed. If you store data close to where needed in distributed architecture, you are reducing latency, because there are usually, when you're communicating in distributed system, there are communication overhead. So when we store data close to where we are needed, we are for some reasons we are highly reducing the latency. But also with distributed systems, we are showing high availability of the system, but also faulty tolerance. Fault tolerance with the fact that we do not rely on a single machine to manage the data. Again, this distributed system can scale as much as it can go, because machines now can join and leave at any time. This gives us an ability to accommodate any changes that comes in the process, be it the changes that goes with the data management systems or the changes with the underlying computing system. Well, also we are experiencing the reduced cost in terms of computing resources. When you have centralized data management, obviously you need a huge data center with very huge computational capabilities. But with distributed systems, that does not really matter. You can have several nodes, each with their special or specific defined computation systems, and they can just share data, retrieve data, read or write. One of very important reasons is flexibility in terms of design choices. Like you can design in either way to fit your requirements, because now we have several requirements. In energy system, we are looking at a certain perspective. And even in energy system itself, design perspective might be different. Someone might want their system to look in a certain ways and some other person in a different way. With these distributed approaches or peer-to-peer practices, we already experiencing some of them in the market. Like there is huge use of peer-to-peer systems in the cryptocurrencies. There is also IPFS, which stores files in peer-to-peer system, and so many other approaches. But the question is, how can we benefit from these peer-to-peer capabilities? Should we implement the database management system on top of peer-to-peer system? Then yeah, if there is a possibility, why not? Now, this drives us to our approach, what we are doing. Now, our system is totally decentralized. Like you have peers that are separate, and we benefit into peer-to-peer overlay capabilities. The system itself is naturally decentralized by nature, highly scalable, like many peers can join the system without a hurdle, but also data sharing and accessibility is guaranteed. Like each peer that has joined in the network can add its own data, but also can fetch data that are being stored from other peers. When you're designing peer-to-peer data management system, it's very important to consider how you are implementing your database engine. Our approach is based in an embedded database engine. And one reason of this is that you are setting your system, your database system close to the node that you want to fetch data or close to the node that you want to read the data. Now, by having this embedded database, you are avoiding also another point of failure, because if you have database engine that is running separate from underlying system architecture, I mean, the database system itself becomes another point of failure. So by having an embedded database engine, whenever your system runs, database engine automatically runs. You do not have to start all of these separately or manage this separately. Also, there is an aspect of data locality. We are saying that in decentralized system, data are stored close to where they are needed. You are getting this from peer-to-peer systems because data, like, are stored in each peer. And whenever you search them, it should be easy for you to run a local query and get the results that you want. Also, this also gives us the benefit of reduced latency, because we speak less about communication latency, like you do not have to do much in terms of fetching data into many peers. Also, by implementing the embedded database engine, you literally have a simplified architecture and maintenance overhead. As I said earlier, if you have a separate database engine that is not attached to the peer-to-peer, to the peer that is connected to the system, that means you have always to consider, how is my database engine working? But when it is embedded to the system, when you're managing the peer, you're also managing the database. You cannot have data stored into your system without considering how do you really query with them. We have seen, like, we can query data efficiently into relational databases. Like, you have a statement, let's say, select all data from a certain user, and then you get all you want. This also has to be reflected into peer-to-peer system. And so data querying into peer-to-peer is also one of the aspects. In our case, we are looking this into 4 aspects. Number one is the query submission interface. We need to give users an interface to which they can submit their queries, but also broadcasting queries. Because whenever you're submitting a query into one peer, you're not fetching data from that peer only. Remember, this is a distributed system. We need results from all the connected peers. And because we are fetching results from several connected peers, we also need ways to merge the data. If it was only you are fetching from a single peer, then yeah, that's simple. But we need to fetch results from all these connected peers. And so we need approaches to which you can merge all the results. For all these 3 to work perfectly fine, it is also important to consider query states or managing the query itself. We need to know, when did we submit the query? Is it now queued or it is already run in a certain peer? We also need to know if it has failed or it is still running. We need to know its position. Is it on returning, like in the process of merging results, or what? So all of these aspects are very, very important into peer-to-peer network. For some reasons, I will skip this. Well, why peer-to-peer? Well, yeah, we've explained this, the power of peer-to-peer already. Now we're speaking, we can connect like so many peers into system. Back in time, it's like we're speaking of tens of peers, but now we can speak even thousands of peers. Well, yeah, perfect. The basic architecture of this system is that you have the peer-to-peer system that helps the peer-to-peer communication, like discover where this peer is located or what data it has. We have the peer-to-peer management platforms, but also bootstrapping aspect, managing and making sure that your peer-to-peer system is always available, because you cannot just rely into your peers. We need bootstrap peers for managing network. And there is not just one single bootstrap peer, because that again could introduce a single point of failure. So there are so many bootstrap peers to make sure that the system operates smoothly and that we can fetch data whenever we need them. On top of it, we said that we need to add database architecture and querying support. Now let's speak a bit of how do we really query data into peer-to-peer system. Depends on your specific design. You can support complex queries, or you can support simple queries. In our case, we're going to demonstrate, okay, we can support some, there is all the limitation, some simple queries and some complex queries, including the operation of basic functions using the SQL statement, like calculation of summation of sustained values, calculating average, minimum, maximum value. But again, you can implement this using graph databases. With graph now, it's a bit easier because when you're fetching data, you can either fetch all the nodes that you have in the system and then you get all the information, or you can fetch all the edges so that you can figure out how data are related to each other. And you can add, when you're fetching edges or when you're fetching nodes, you can add your condition that you want. For instance, we are fetching data for user for power consumption for household, and you want to specify power consumption should be greater than something. You can always specify that in graph databases. So all of these aspects have to be considered when you're designing peer-to-peer data management system, and it has been considered in our case. Well, that is about writing a query. What kind of a query you can write and what kind of a query you can submit to a system. There is also a question of how you can broadcast a query into entire system. We have a pointer, right? Yeah, there's a pointer, perfect. So for each query that we are defining, for instance here, you can read it, right? Well, for instance here, we have a simple query, let's say select all from TB1. That is our query statement. For each query, we need to define the time to live. Like how long can we wait for results to come back? This is very important because if your peer-to-peer is huge and you don't set the time to live, it might run forever because getting all these results from thousands of peers, we don't know how long you can wait. And remember, we are considering very large scale data. So it's very important that you set time limit, but there is always a consequence. The higher the time to live, the higher the amount of data you get. The lower the time to live, the lower amount of data that you get. So there is always a trade-off depending on the amount of data that has been stored or the amount of data that you want to retrieve. Also, to be able to manage the query, for each query that we are submitting, we are introducing an identifier for each query. We call it UKI. UKI allows us to know or track the query itself. Where is it? What is its current state, knowing if it has failed or what, but also it helps us to fetch the result itself. For instance, look at this. Yeah, this shows a good example. Now we have a user here who is submitting a query into a certain peer. Remember, into peer-to-peer system, you only need to know the identity of a single peer, and you submit query to that peer. That peer now is responsible for forwarding queries to all peers that are connected into your system. Now we have a peer with ID AA1. Once this peer receives a query, it is responsible for forwarding to all the peers that are in its routing table. Routing table are the peers to which it can communicate to directly. And each peer that is connected to a system has its own routing table. So for each peer that receives a query, it has to forward to its routing table. But again, that's a bit political, right? Because some peers can receive some data twice, right? Because you belong into more than one routing table, because there is no rule that you only become to a single routing table. So yeah, an example is here. So peer AA1 forwards a query to BB2 and the CC3. And whenever we are forwarding a query, remember we have introduced the time to live. Whenever we move from one peer to another, whenever we increase the hop, we need to reduce the time to live. This again, you can set a reduction factor. In our case, the reduction factor is 0.75. The reduction factor can also be different depending on how your system is huge or how the number of peers that you have or how far you want to go. Because you can say like the reduction factor be 1 if you have 100 peers. That means in 100 seconds you can access all the peers. So it really depends with your underlying system and how much data you also want to fetch. Now you can see that in a table query, in a second peer, as we go to second peer, we have the same query statement, but time to live now is 9 seconds. Remember, initially we started with 12 seconds, but now we have 9 seconds. The UQI value stays the same. This has also been the same to the second peer because they are all on this first hop. So the time to live here is 9. When you are going into a second hop, time to live reduces to 6.75. Remember, you have to set your own reduction factor. This can change depending on the system, but UQI value stays the same. Now, in this case, we are forwarding our query to DD4. Now, DD4 wants to forward its query to its routing table. one of peers in its routing table is peer CC3. Now CC3 has to check, do I have this query already in my peer? Have I run it? This is the importance of having query states. We need to know if it's already run in our case or not. So if it is run, on this case, you can see that the same query is submitted to CC3, but also the same query was already submitted to CC3 with the same UKI value. On this case, we have to discard the second query. Now we will not run the second query because we have already run it. But if UKI value is different, then we'll just run it in our system locally. Well, that's how technically it's broadcasted from one peer to the other peer. One aspect that's very important to consider is results merging. Like we can run with what this query to probably 100 of peers, but how do we get these results back? There are two ways to do this. One way is by focusing on the initiator node. Like for each peer to which they receive the query, they can forward the results directly to the initiator node, the first peer to which received the query from the client. Or another approach is by looking to overlay nodes. Like I send a query to a certain peer. Now that peer, on merging the result, they have to send the results back to me, and I forward back to the results where I received the query until they arrive to originator node. Now the originator sends the results back to the client. Now there are these approaches. The consequence of the approach number one, for each peer to return results back to an initiator node, is that we are overloading the initiator node to have this task of managing all these results. But by relying on overlay nodes, like you can see the load balancing, like each peer, they are having its routing table and they merge results at their autonomy. In our case, we're opting for overlay just to improve our performance. We do not want to overload a single peer, but it is also a possible approach. And of course, it might be an easy approach to implement because it's just direct. The query state, I think I've spoke a bit about this. If you are an originator peer, your state could be in 4 states. Either you're on a queue, waiting to run, waiting to run, or you have already been executed and you're waiting for time to leave in order to return results, or you have completed querying your results and so you're waiting to go back, or you have failed somewhere. And fail, we can experience it on queue or when you run it locally. And so we need to track this. If a query has failed, we need also to probably fetch some reasons why and blah, blah, blah. Another way to manage them is an overlay node. An overlay node is not an originator node. These are the nodes which received a query from a certain node. These are queries that have to add a state sent back so that we check that if we have sent back the results or not. The rest of states stays the same. Now that's basically what we're working on. Like theoretically supposed to work that way. Like we have these peers and then we're receiving queries, we're broadcasting to all the peers, we are merging the results and then results goes back to the client. Where can we really apply this? I don't know if Conrad, you're going to speak about this tomorrow, but one of the cases that we have looked at the challenges that Conrad have experienced when collecting data from the DSO, it was just a case of 6 DSOs, right? In our case, it will be like 6 peers. That's literal. If we consider to how the system can perform, with 6 peers, we literally can fetch everything that is stored because they're just few peers. Because as I said earlier, we can expand this to even thousands of peers. Now, one of the challenge, Conrad, feel free to comment later, not now, later on this case. So data are collected from multiple DSOs and they are collected individually. Like each DSO has autonomy to collect their own data. Data that is centrally managed is data about failure, right? These are centrally managed somewhere, and so we can access them directly there. But all other data about operation, cable stuff, that's what we were looking on, they're collected individually. So if you want to fetch this data and work on something, you need like to go through a lot of procedures, right? Because you're collecting them, they're already in different shapes, different format. And so before using them, you need like to clean, reshape to fit into what you want to do. But again, collecting from them, it's also, it can get political because you have like to sign a lot of documents to get access to this data. And also some peers, some DSOs may be hesitant of sharing this data for business secret reasons or confidentiality of the data items themselves. So that's literally what is happening into the industry, getting data from the DSO. Theoretically, we should be able to store this data into peer-to-peer. And whenever you want data from the system, you should simply submit a query. I want certain data, and then you get the data which are merged from all DSO. Now, getting that into reality also has to be some sort of some political. I don't know, Roberto can do something here. Now, well, I feel like we should directly go to to see how the system works by itself. Let's look at a demo. I want to run few peers. We're finalizing this. Okay, perfect. So we have, I hope you can see this. I will explain some of the, because it may not make sense looking at all these files and scripts. So we have the system already compiled. One thing that we're going to do is to launch a certain number of peers and probably store certain number of records. And because we also need to consider time aspects here, because we cannot test 100 peers now. I'm not sure how long it's going to run, but Massimo tried there. He'll give us feedback. He's running 1,000 peers. I'm not sure. Massimo, are you still running it? Oh, okay, perfect. All right. Well, so I'm running script. Yeah, should I take a look at that? Okay, yeah, perfect. So let's take a, yeah, we have 1,000 peers running there because I was about to run 100 peers. I think it would make sense looking at 1,000 peers. How does it work?
I need to connect.
Yeah.
This one. And then go here. Now I can this one. Yes, I can share this. Even less, because the servers are already running, so it should. So as you can see here, we have 1,000 server instances already up and running. You see IDSS followed by a number. We have 1,000 of them. And more or less, we have about 10 records on each different server for about just slightly less than 10,000 records distributed over 1,000 servers. So I can retrieve them all. Imagine that I want to put a query to retrieve all data from a specific table. And the query is this one in the specific. select star from table user, which is a table which store information related to the users. Okay. So, sorry? Let me try. This is for searching. So
Yeah, doesn't work the touchpad.
no, it won't work.
This menu?
No, but this enlarges, but no more than
This one.
No, this one. Okay. So something more?
Yeah. Better.
Okay, let's go even more than this. It's okay now? Okay. So I run this distribute query and I say I allow 20 seconds for the query. Okay. So what you see here is that this client is contacting one specific server at that address. And you see here that the exchange is happening, is in place. This is the security. There is a security callback involved. The client is verifying the identity of the server is verifying the identity of the client, and there is mutual authorization. Then, once they are authenticated and the authorization is in place, the query is actually forwarded to the server, which then execute a distributed query, forwarding the query to the 1,000 different services. You can imagine that each server instance may be geographically located in an arbitrary country. It doesn't matter. And then the distributed result is assembled and sent back through the servers in a specific way that we have designed back to the originator server. And then we have here one numerical identifier. UQI is unique query identified, which allow us to distinguish each query. So then we can get back the query result for that specific query identifier. Okay, so here we get back the results and we can actually see the results. So as you can see, we got back this record set. So every record is made of 2 strings, 2 integers, and 1 float. And we have retrieved, as I told you, about 10,000 records from the 1,000 distributed server instances of the InnoCyPES distributed storage service. And you can see here all of the records. User, so first name, last name, user ID, contract ID, and power associated to the contract. I mean, we just used a very simple schema for this. We have a couple of tables, one for the user, one for consumption, and we retrieved those records. And those are about 10,000, okay? So think about how simple is this. Imagine the amount of work that you have to perform if the servers are actually independent servers. You have to assemble and run 1,000 queries, one for each server. And then you have to work on the results. You have to merge the results. Now, let's do something even more interesting. I don't want to retrieve all the records, but I just want to know, for instance, this one, So I want to know the minimum power, the maximum power, and the average power from the user, or maybe the consumption, blah, 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 stuff like that. So the minimum, maximum, and average power. I can send back the query again. 20 seconds are more than enough. I will show you what happens if I use less than 20 seconds in a moment. But for now, let's just see this example of complex query which involve aggregation operators. Let's wait just a few seconds more to allow the 20 seconds to elapse. Okay. And so we get back our results. So we got one record in return, which includes the minimum power, 2 kilowatts, the maximum power, 9 kilowatts, and the average power, 5.48. So this has been done computing these statistics in a distributed fashion over 1,000 instances. Now, I will show the same query that we ran before, running the query for less than 20 seconds. Where it is? Okay. So say that now we allow to run for only 10 seconds. So we are the user. We decide how much time we are allowed. We want to wait. Of course, the more we wait, the more the results that can be collected. So let's see how many records we get back by using 10 seconds instead of 20. For exactly the same query we did before, and the result was full, all the records, 9,980. Right now, oh no, we got all of them again. No, 9,890. Okay, that was the total number of records. So let me use less than 10 seconds, 5 seconds. 10 seconds, it's already enough to get all the results back. So it's very fast. Let's wait for just 5 seconds. And let's verify how many we're able to get back. Okay, right now we got back 5,440. So we decide the time limit we allow our query to run in a distributed fashion, and it's a best effort procedure. And if we want to limit the time, we get back not all the records back. It's up to us. Anyway, this is not a big problem. We are allowed to use as much time as we like because the query is not a synchronous query. So we simply say, initiate the query, get us back an identifier, and later, asynchronously, we can check the results. However, if we are in a hurry, in 5 seconds, we may get half of the total records from the 1,000 servers. It's a very nice result, I think. Okay, so those are just sample queries just to show you that the system is in place, works, can actually be used. It's, of course, it's not production level, it's a research prototype, but you get the idea. We can do this. Thank you.
Right. So generally, that's what we are pushing, and currently we're working on doing the same method using the graph databases. See if we can get benefit of graph databases. For obvious reasons, there are benefits, and also we have a different technology stack implementing all of the same theory of query submission, query broadcast, results merging, and then see if there are differences in performance. That's all we got for you today. Let's see if we have questions and discussions.